Okay, so let's do an example with equilibrium constants and cell potentials. Okay, so what we're going to do, this example here is two parts. We're going to calculate the equilibrium constant for this reaction right here. Now, you remember that earlier on in the podcast, we calculated the cell potential for this cell, and we found that the standard potential for that cell is, let me look back at my notes here. What did we find for that? The standard potential for this cell is 0.04 volts. Okay, so using this information here, we're going to calculate the equilibrium constant for that reaction. Part B, the question is, what are the equilibrium concentrations of Fe2 plus and Cd2 plus if the initial concentrations of both were 1 molar? All right, guys, let's go through and do this. Well, for the first one right here, okay, let's see if we can insert a blank slide. Okay, we're going to put a blank slide right here. All right. To find the equilibrium constant, we're going to apply the equation. The natural log of K is equal to N, which is the number of moles of electrons transferred, times the standard potential for the cell over 0.0257 volts. Okay. If we go back here and look at this reaction, we saw that N is going to be 2, because there's 2 moles of electrons transferred. The standard potential for the cell was 0.04 volts, and this divided by 0.0257 volts, we can see that the volts here are going to, of course, cancel out, and then we're going to be left with 3.1. So the natural log of the equilibrium constant for this reaction is equal to 3.1. To find K, we're just going to raise e to the 3.1 power, so K is going to be 20 is what we get. So we can see that this reaction here favors formation of products because K is greater than 1. So the equilibrium constant for this reaction is 20. Okay, so keep in mind, guys, even though I have this reaction written here as the arrow going this direction, really this reaction is in truth reversible, and so it goes both forwards and backwards. So here's the voltage for that cell. K for that cell is going to be 20. All right. Now part B is this. What are the equilibrium concentrations of iron 2 plus and Cd2 plus if the initial concentrations were both 1 molar? An excellent question, guys. Now, if I were to ask you how to figure this out, we have an equilibrium constant and we have initial concentrations. How do we figure it out? Well, let's make an ice table, everybody. So here we go. We've got our reaction. Iron plus Cd2 plus is going to go reversibly to give us iron 2 plus Cd solid. Now, really quick, guys, if we wanted to write the form of the equilibrium constant for this reaction, I'll just write it up here. K is going to be equal to, if you look here, the products, we have iron 2 plus, we have cadmium. The iron 2 plus really is all that matters because the cadmium is a solid and we don't care what the concentration of that is because it does not change. So it's going to be the concentration of iron 2 plus to the first power divided by the concentration of cadmium 2 plus also to the first power. Okay? So let's go in here, we're going to make ourselves an ice table, and we're going to fill in the things we know. Well, if we read the problem, it says the initial concentrations of both iron 2 plus and cadmium are both 1 molar. So the initial concentration here is 1, and the initial concentration here is 1, and then this we don't care about at all throughout, actually, because these concentrations of the iron, the solid iron, and the solid cadmium do not change. Okay, let's fill in here the changes. Let's think. What happens to the concentrations of the cadmium ions and the iron ions as the reaction proceeds? Well, we know that K for this reaction is 20, which means it's product favored, which means as the reaction proceeds, cadmium 2 plus is going to get used up, and we're going to, because this reaction goes forward, the forward reaction is favored. So we're going to use up cadmium ions, and we're going to make iron ions. Because cadmium gets used up, the change is minus X. And the change over here is going to similarly be plus X, and then so at equilibrium we have 1.0 minus X, and here we have 1.0 plus X at equilibrium. if you plug these values here into our equilibrium constant expression, K is going to be equal to the concentration of iron, which is 1.0 plus X over 1.0 minus X, and this whole shebang is going to be equal to the value, which is 20. If we go through now and we solve for X, which is going to tell us the change in concentration, okay, X gives us 0.9 molar. All right, so that's X here is going to be the change. So once we've reached equilibrium, the concentration of cadmium ions in the one cell at equilibrium is going to be 1 minus 0.9, which is going to be 0.10 molar approximately, and the concentration of iron 2 plus is going to be 1 plus 0.9, which is 1.9 molar. So there we go, guys. How we can use the potential of the cell to figure out concentrations and the equilibrium constant for that system. So that's going to be the end of the lecture for today. Hopefully you guys are able to find this on YouTube. Now, because we had kind of a short lecture, in addition, because we didn't cover electrolysis, we have to do that in class Friday. And so what I'd like you guys to do in your book, tack on to the last assignment these problems. You're going to add problems 41, 43, and 45 to the assignment. 45 in particular is a very easy problem. 41 and 43 are not very difficult at all. They just require you to do a little bit of thinking. And for these things, whenever appropriate, guys, draw yourself a picture, because on the AP test, it is very likely you will have to sketch an electrochemical cell, and you need to make it reflexive and second nature for you. So that, guys, is the end of the presentation. Have yourselves a good day off tomorrow here during STAR testing, and I will see you guys Friday in class.